All right, tonight what we're going to be talking about are gas laws, and this will be the final unit of the semester. All right, so there's some characteristics that you need to understand about gases. Gases, even though we don't feel that they do, they definitely have mass. So if you think about like carbon dioxide, okay, carbon dioxide is a gas, it does have mass, even though it's very, the thing is it's got a low density, so we don't feel its mass compared to like if we pick up the stapler, we can feel its mass because it's extremely dense comparatively, but it still does have mass because if you had carbon dioxide, obviously you could calculate its molar mass. It is also easily compressed, so we could change its volume readily. It will completely fill their containers. So if I put it in the container the size of a vial, small vial, or I put it in the container the size of this room, it would fill up the entire space of it. It will diffuse rapidly, meaning it will spread out quickly. It exerts pressure. Pressure is caused by collisions with other things. So collisions. Okay, so a gas, when it collides, let's say with a wall, okay, here's my little gas particle, when it collides with the wall and bounces off, this right here is the pressure. And sometimes I'll refer to it as a pressure event. So anytime a gas particle collides with something, it's going to be exerting pressure. It also depends, its pressure depends on the temperature. If it has a greater temperature, that means it is moving faster. And we demoed that earlier in this year. So if it is moving faster, what's going to happen is it's going to be able to push more and force on this point than if it was moving slower. Right? So it would be exerting more pressure the faster it's going. So the higher the temperature, the more pressure it will exert. It has perfectly elastic collisions. Now, this is totally not true at all, but what perfectly elastic collisions is when two particles, let's say, collide into one another, what they do is they bounce off of each other perfectly, and no energy is lost but through heat when they run into each other. So normally when we bounce a ball, let's say, we bounce a ball, some energy is transferred to the floor through heat, through friction, whatever. Okay, so it ends up losing all of its energy that it had, and it eventually will stop bouncing. Okay, with a gas, what would happen is if I drop that ball, if it was a perfectly elastic collision, no matter what, that ball would 100% always keep bouncing back and forth, up to the exact same level, and it would never get higher, it would never get lower. It would be the exact same amount. That's what a perfectly elastic collision would happen. And then they are not attracted to one another. So if I have one gas particle floating by another gas particle, they're not going to be attracted to one another by charges or anything like that. They don't even like see each other's presence. They're not attracted, I guess, and nor repelled. All right, the variables that we're going to be using in this class for this unit are these four ones. Amount. The amount in this class is moles. And I know it's weird, but it's abbreviated in the formula as N. Little m would be meters. If it was italicized, it would be molality. If it was capitalized, it would be molarity. So in this class, moles is abbreviated as N. Okay, volume. Okay, these are also all things that change the gas's behavior. So if I change the amount, if I change the volume of the gas, different volume units would be liters and milliliters. It is capitalized, symbol is a capital V. Temperature, which is abbreviated as T, is measured in a unit called Kelvin. And Kelvin is very similar to Celsius, and it's a very easy change between Kelvin and Celsius. Unlike Fahrenheit to Celsius, which is like 5 nines plus 32 or whatever it is, Kelvin, all you have to do is change whatever your temperature is in Celsius and add the number 273. So if I had, let's say, 10 degrees Celsius, that in Kelvin would be 283 Kelvin. And notice that I don't say degrees Kelvin, it is just straight out Kelvin. And we'll go into the why of why we need to be in Kelvin as opposed to Celsius. I guess we could go into it now. So why do you need to be in Kelvin versus Celsius? Well, the problem with a lot of these equations, and I'll show you one, is like, let's say V over T. Okay, and let's say I had V over T. So these are like one equation that we're going to be dealing with in this class. If I had a volume, let's say, of 2 liters and a temperature of -2 degrees Celsius, and then I wanted to say, hey, what's its volume when it is 10 degrees Celsius? If you do the math for this to solve this, you're going to get a negative volume. Okay, that is absolutely not possible. So what they do is they created a system with the Kelvin system where it will never, ever, ever, ever go negative. So a Kelvin, there will never be a negative Kelvin temperature. And I'll explain that in another slide. All right, so then we also have pressure. Pressure will change also the behavior of a gas. There are quite a few units for pressure that you're going to need to know. Atmospheres, which is abbreviated as ATM, pascals, kilopascals, and millimeters of mercury. There's also torr, T-O-R-R. Just to let you know, millimeters of mercury and torr are very similar. They actually are the same thing. They're just different units, I guess. But 1 millimeter mercury equals 1 torr. Pascals and kilopascals are the same. This is just 1,000 with the kilo. It's 1,000 pascals. And it really depends on what science you're studying. Typically, if you're studying like meteorology or weather, you're going to use millimeters mercury. If you're studying physics, you're going to be pascals or kilopascals. And then if you're studying chemistry, they tend to use atmospheres. So we kind of use, depending on the area of science that you're studying, it depends on what unit of pressure you're going to be using. All right, this is another thing you're going to absolutely 100% memorize. If I say the term STP, what does that mean? Well, scientists created this standard temperature and pressure, okay? So if we ever say STP, I am literally telling you the pressure and the temperature at that time. The temperature, if I say ST, would be standard temperature. What is that defined as? 0 degrees Celsius. So what does that mean in Kelvin? Remember, all you have to do is take your Celsius degrees and add 273, so that would be 273 Kelvin is standard temperature. Standard pressure is what is defined as what is the pressure or atmospheric pressure at sea level, which would be 1 atmosphere. If I said 1 atmosphere, that is also going to be equal to 760 millimeters of mercury, or 101.3 kilopascals or kPa. Okay, and we'll go into these conversions later, but by me saying standard pressure, because it's equal to 1 atmosphere, I am also saying it is equivalent to those. So you could use any of those three. Okay, and for all of our calculations, we have to be in Kelvin. So there's this thing called absolute zero. What's crazy is that if you think about temperature, okay, temperature is the measurement of movement. So what happens when all movement ceases? Well, then you don't have temperature, right? Because if you don't have movement, then you can't have temperature. So what is that temperature? Well, it actually does exist. What it is it's known as OK, which is 0 Kelvin, and which is negative 273. So this is the lowest possible temperature ever. Okay, why? Because once again, temperature is the movement of these particles. If there is no movement, then that is the lowest possible temp you can get to, which is 0 Kelvin or negative 273 degrees Celsius. So notice, because motion had stopped at 0 Kelvin, I can't get lower than that, so therefore I will never be negative. And that is once again known as absolute zero. We have gotten to a millionth of a degree in Boulder, Colorado, but we haven't gotten lower than that since. And it's only been in lab conditions. We've never been able to do it. It's not happening outside in nature, right? Okay, so atmospheric pressure, this is where I'm talking about standard pressure, so SP. You can use any of those. So if I tell you that, hey, the gas is at standard pressure, you can use at 1 atmosphere, 101,300 pascals, 101.3 kPa, or 760 millimeters of mercury, whichever one you want or whichever one helps you out with the problem more. But you will have to have these known, and they are all equal to one another. So let's just do some conversions. So if I give you 756 millimeters of mercury, and you're going to have to be expected to do this on the test. So I need it in atmospheres, let's say, for whatever reason for my equation. So I'm going to do 756 millimeters of mercury over X ATM, or atmospheres. That is equal to, I'm going to set up a proportion. I know from the previous slide that is 760 millimeters of mercury for every 1 ATM. Or 1 atmosphere. When I cross multiply and round to sig figs, I get 0.995 ATM. Okay, for 4.5 atmospheres, and I want to know kilopascals, I'm going to set up a proportion again. You're always going to be setting up proportions for these pressure conversions over X kPa, and that is going to be equal or proportionally equal to 1 atmosphere for every 101.3 kPa. So once again, you butterfly cross, or whatever you guys say, I say cross multiply, and you get rounded to sig figs, you get X equals 460 kilopascals. And then the last conversion that we're going to do between pressure units is 65.01 that's a 1, kPa equal over X ATM, and that equals 1 ATM, 101.3 kPa. Notice when I'm setting my proportions, the units on the top have to be the same and the units on the bottom have to be the same. Doesn't matter which way you do it, but as long as they're the same, you're fine. And then the numbers correspond. So when you cross multiply and round to the correct number of sig figs for that one, you get x equals 0.6418 ATM. All right. Now to do Kelvin to Celsius and Celsius to Kelvin, to do Kelvin to Celsius, you're just going to take your Kelvin degrees, or temperature, not degrees, minus 273, and you get 294 degrees Celsius. And to go from Celsius to Kelvin, as we've done in some previous slides, you're just going to add 273, and you get 729 Kelvin. Note once again that Kelvin is always going to be 273 degrees, not degrees. The number is going to be 273 higher than that of the degrees Celsius. So therefore, Kelvin will always be a larger number than Celsius. All right, hopefully you have a basic understanding of this information. Have a great evening.